Okay, so resuming our chapter 1 lecture, we left off discussing elements and compounds. We're now going to discuss pure substances and mixtures. So we're taking our elements and compounds and we're mixing them together, and we're looking at how to classify mixtures of pure substances. So what is a pure substance? That term is tossed around a lot. A pure substance is matter with a fixed, definite composition. For example, water, H2O liquid, has a defined chemical formula with a definite composition of elements. Pure substances have a fixed composition and a fixed amount of each component element. So for example, in water, we have 2 hydrogens and 1 oxygen. And water always has the same amount of hydrogen and oxygen. Pure substances can be either elements or compounds. Now, the key feature of a pure substance is the composition is independent of source. So if we think about water for a moment, if you have pure water, whether you get it in a glass, as a dewdrop, or in a lake, if you have isolated pure water, the chemical formula for all of these samples of water will be H2O liquid, right? Pure water always has the same chemical formula. So, are these water molecules in each of these water samples different? Is there any difference in the chemical formula or composition of these water molecules? Is there any difference whatsoever? Do they look different to you? And don't be shy to respond in the chat. Oh, exactly, there's no difference between these water molecules. The chemical composition of pure water is independent of the source that you've isolated it from. This is nice for chemistry because it doesn't matter where we buy our chemicals from. If they have the same chemical composition and the same chemical formula, we won't have to worry about any inconsistencies. One moment, allow me 1 second just to reset OneNote. Okay, so a mixture is a combination of variable amounts of 2 or more pure substances that are not chemically bonded. So we just have 2 or more pure substances mixed together. There's no chemical bond between these pure substances. Mixtures have a variable composition and contain varying amounts of each mixture component. Components of a mixture, again, I can't stress this enough, are not chemically bonded. Now, there are 2 types of mixtures that we'll encounter. Homogeneous mixtures, which have a consistent composition and no phase boundaries. So for example, aqueous sodium chloride or salt water. So just to show how this mixture would work, if you have pure water, so if you have pure water and we take a cube of sodium chloride and we dissolve our cube of sodium chloride in water, what we will see is that we'll get a nice clear solution of sodium chloride aqueous in water. So we have a perfectly clear solution. So wine would also be a homogeneous mixture because it has consistent composition throughout. We don't see any clear evidence of solid precipitating out of the solution. We don't see any clear deposits of solid in our mixture. We just have consistent composition throughout our mixture. No matter where you look in the solution, no matter whether you look at this portion here or this portion here, we have the same composition throughout. Does that make sense? Perfect. So in contrast, a heterogeneous mixture has an uneven composition and there exists a phase boundary between components. So what's an example of that? If we have lead chloride solid in water, well, if we look at our picture, we'll begin to see what's going on. If you try to put lead chloride in water, you'd have this chunk of lead chloride solid at the bottom of your flask, and we'd have water above our solid sample. As we can clearly see, water and lead chloride have a different chemical composition. Throughout our mixture. Now, different chemical composition is one factor for heterogeneous mixtures. The other factor is the existence of a phase boundary. For example, if we have solid water in liquid water, for example, so we have an ice cube floating on top of our liquid water. So we have a solid ice cube floating on top of our liquid water. We see that there is a clear phase boundary. And what is a phase boundary? It's a difference in physical state between components of a mixture. So the way I like to remember this is if I go from my liquid water sample to my solid water sample, are these two samples the same? Is liquid water the exact same as solid water in terms of physical state? Do we see the same or different physical state? Can you tell the liquid water apart from the solid water? Yes, you clearly can. So this is a heterogeneous mixture where we have two components with the same formula, but different physical state. There's a clear phase boundary. Okay. So let's keep going from here. Now there's a special type of homogeneous mixture that we call a solution. So a solution is a homogeneous mixture where one or more pure substances are dissolved in one or more other pure substances. Now, we call the components of solutions two unique terms. First, the solute is the minor components of the solution. It is the species dissolved in another component. One common symbol that you'll see for solutes in water is the aqueous symbol. AQ means the species is dissolved in water. The other component of a solution is the solvent, which is the major components of the solution. It's the species, or it's the set of pure substances doing the dissolving. So for example, let's suppose we have some water and we have, suppose we have some water and we want to dissolve in that water. Let's use ammonium chloride, sure. So we place and we dissolve our ammonium chloride in water, and that in turn generates a solution where our solvent is water and our solute is ammonium chloride. So our ammonium chloride is our solute and water is our solvent. Does this make sense to everyone so far? Any questions so far? Okay, let's keep going then. Just as a recap for classifying matter. So the first question you'll ask yourself, is the composition variable or fixed? So mixtures have a variable composition, while pure substances have a fixed composition. The reason for that, and just to elaborate on this idea of variable composition, you can change the amount of each component that you mix together in a mixture. A pure substance has a fixed amount of each component element, and most importantly for pure substances, the components are chemically bonded together. Now, for an element or compound, a compound has two or more different elements. Now for our mixture, the main difference between a heterogeneous and a homogeneous solution is that a homogeneous solution has consistent composition throughout. An example of a homogeneous solution would be tea with sugar dissolved in it. So let's try to apply these classifications and let's deal with the following. So we're asked to classify the following as a homogeneous mixture, heterogeneous mixture, or a pure substance. So looking first, sulfuric acid dissolved in water. So when we see the keyword dissolved in, what does that make us think? Do we have a mixture or a pure substance? Do we have a mixture of things, or do we have one pure substance? We have a mixture, okay? And dissolved in tells us we have what kind of mixture? The word dissolved, what does that tell us? Homogeneous. So dissolved in indicates that we have a solution and it's a homogeneous mixture as a result. Okay, perfect. CH3OH, otherwise known as methanol, is this a pure substance or a mixture? Is methanol a pure substance or a mixture? Yep, it's a pure substance. Perfect, perfect. So now that we've done a guided example together, let's take a moment. Let's open up Canvas Quiz 1.9, and I'd like you to try to classify the following as either a homogeneous mixture, heterogeneous mixture, or a pure substance. So don't be shy to submit your responses via Canvas or using the chat function in Confer Zoom. Ah, sure. Sure. I can scroll back up to the recap. So let's get a few more responses in the chat or via Canvas, and then we'll discuss momentarily. So I'm seeing a lot of reasonable responses so far. So let's talk about this. So carbon dioxide, is that a mixture or a pure substance? Is that a mixture or a pure substance? Pure substance, exactly right. Okay, let's look at the following compounds. We have this aqueous symbol. What does the aqueous symbol tell us? What does the aqueous symbol tell us? It tells us we have a solution. And is that, yep, aqueous also tells us that it's dissolved in water. Yep. And does that mean we have a homogeneous or heterogeneous solution? Does that mean we have a homogeneous or heterogeneous solution? Homogeneous, exactly right. So this is a homogeneous mixture. Perfect. Any questions on these examples? Any questions on these examples? If not, let's keep going then. So this is an advanced example. So let's break this down piece by piece. So let's spend about a minute to 30 seconds on this first question. So this is labeled an advanced question in Canvas. And let's start off first and foremost by looking. Yeah, the Canvas quizzes are just graded on participation. So for advanced question 1.10, let's ask ourselves first and foremost, which of these two mixtures, the one mixture A on the left or mixture B on the right, which mixture is homogeneous, A or B? Which mixture is homogeneous? And this is pretty quick. A is the homogeneous mixture. We clearly see a phase boundary, a separation of phases in B. A is consistent throughout. Now let's take a moment and I'd like you to start for mixture A. I'd like you to list the pure substances in mixture A and classify each of these pure substances as an element or a molecular compound. And let's take a few minutes. You're more than welcome to try to submit your responses via Canvas or via the chat. Either is fine with me. And keep in mind that different elements will have different colors in the following picture. And let's get a few more responses for this question, and then we'll discuss in about a minute to a minute and a half. Okay, so let's start. We see a clear consensus that carbon tetrachloride, CCl4, is a compound. We see clearly two different elements covalently bonded together. So if we look at octane, so looking at octane, which has the formula C8H18, is octane an element or a compound? Is octane an element or a compound? Does everyone notice how we see two different colors representing two different elements? So then octane would be a compound that we put the symbol M for molecular compound. Does this example make sense to everyone so far? Oh, that's a typo. I'll get that corrected in a moment. Does this portion make sense so far? Let's take a look now and let's try to classify the pure substances in mixture B and classify each pure substance as an element or a compound. So let's take a look at mixture B. Let's take about a minute to a minute and a half, and let's try to classify each of these components as elements or compounds. These problem-solving exercises, your participation on Canvas, it's purely participation. Yeah. Octane is a compound because it has two different elements covalently bonded together, as indicated by the two different color circles found in its molecular depiction. Does that make sense? Perfect. Let's get a few responses for the components of mixture B, whether these components are elements or compounds. Let's try to get a few more responses and we'll discuss in about 30 seconds. So let's talk about it. So first and foremost, we have gasoline. And is gasoline an element or a compound? So looking at our depiction of gasoline, do we see a single element or do we see multiple elements bonded together? Gasoline is a compound, exactly right. So we'll put an M for molecular compound. And water, H2O, is that an element or a compound? Is water an element or a compound? Water is a compound, exactly right. It has two or more different elements covalently bonded together. Okay, let's keep going now. And let's talk next about chemical and physical properties. So elements and compounds can react and convert to new compounds or decompose their component elements via chemical changes. So a chemical change is a process that changes the chemical composition of matter. Chemical changes are overwhelmingly going to be chemical reactions. So in a chemical reaction, our reactant pure substances will make and break chemical bonds to form new pure substances that we call products. These products have a different chemical formula, a different arrangement of chemical bonds, or a different number of atoms. However, one thing that's really key is that even though we're making, breaking, and rearranging our atoms in forming new chemical bonds, the total number of atoms of each element before and after a chemical reaction remains constant. Atoms are conserved. So we describe chemical changes. We portray chemical changes via chemical equations. So chemical equations will describe the conversion of reactants to products. So first and foremost, let's talk a little bit about reading chemical equations. All of the species on the left-hand side of our reaction arrow are reactants. These are the species reacting in our chemical equation. The products, or any species produced from the chemical reaction, are found on the right-hand side of our chemical equation. Our reaction arrow indicates the reactant and product sides of the chemical equation. Now, next to every single species in our chemical equation is the state symbol. So notice how every single compound or element has a state symbol. This, of course, indicates the physical state of each substance. S for solid, L for liquid, G for gas, AQ for aqueous. This will be a central point in later chapters. Now you may notice that we have numbers in front of each of our compounds. These numbers are known as the reaction coefficients, and these indicate the number of each molecule, atom, or compound participating in the reaction. So a 2 tells us we have 2 molecules reacting. Any questions on chemical reactions and chemical changes? This is just a brief overview to get everyone exposed to how we represent chemical reactions. Okay, let's keep going then. Let's look at evidence of chemical changes. Let's look at evidence of chemical changes. So chemical changes can be indicated by the formation of gas or solid precipitates, color changes, or the generation of heat or light. So for example, we see a few depictions, one where we have a piece of reactive metal generating bubbles when it's placed in water. We have the classic sodium and water demo, and we have the mixture of two solutions to generate a solid precipitate. Now, there are some physical changes that absorb or generate heat, and we'll talk about those more in later chapters. Now, chemical properties are inextricably linked to chemical changes, and they're a property observed when a substance changes chemical composition, or it's a property observed when something undergoes a chemical change. So chemical changes fundamentally concern reactivity. So we're trying to answer the questions, how does the species react? What occurs during the reactions? For example, an example of a chemical property is that alkali metals react vigorously with water. Another example of a chemical property is that combustion of gasoline generates heat. So in this case, we're describing the behavior of substances or chemical reactions, or properties associated with a substance when it undergoes a chemical reaction. Now, in contrast to chemical properties and chemical changes, physical changes do not change the chemical composition of our substance. So common physical changes are one-phase changes, when a sample changes from one physical state to another with no change in chemical formula. So a classic phase change that we often see a lot is with dry ice. We are going from carbon dioxide solid to carbon dioxide gas in sublimation. As we can see, is the chemical formula changed by this process? Is there any change in the chemical formula? Has anything changed about our chemical formula? No, the chemical formula is unchanged. Okay, another example of a physical change is mixing or dissolving two or more substances. We call this solubility in the case of dissolving substances. So for example, if you take sugar, which is C11H22O11, and we dissolve it in water, we are in turn generating aqueous sucrose with an aqueous symbol. But again, has our chemical formula changed? Has our chemical formula changed? Yes or no? No, it's unchanged. So when a substance dissolves, the chemical formula does not change, only our physical state. So we're going from solid, liquid, or gas to the aqueous physical state. Now, in terms of physical properties, physical properties are properties exhibited by a substance without changing its chemical composition or chemical formula. So let's try to list a few physical properties. So for example, if we have a block of copper, can I record its mass? Can I put this block of copper on a balance without changing its chemical formula? Can I figure out the weight or mass of this copper block without changing its chemical formula? Yes. So one example would be mass. Can I measure this copper block and figure out how much space it occupies? Can I figure out the volume of this copper block? Yeah. So we can also figure out its density. Can I look and observe the color of this copper block without changing its chemical identity? Yep, we can look at the color. Other examples, so let's suppose we have an ice cube, so solid water. Can I figure out the temperature when this solid water begins to melt? Can I figure out its melting point? Yep. So these are a few examples of physical properties. So why does this matter? Well, mixtures are commonly separated using physical changes. So in separations, what we're doing is we're leveraging the physical properties of a substance to differentiate and separate substances without changing the chemical identity of each mixture component. So there are a few separations that we commonly do in the laboratory. Separations based on solubility that we call filtration, where we're separating a solid from a liquid or a solution. And distillation, where we are separating two or more liquids. And distillation separates compounds based on boiling point. In each case, we are utilizing a physical property and differentiating compounds based on their physical properties. Does this make sense to everyone so far? Okay, perfect. So let's keep going now. Let's do a guided example where we classify the following changes as physical or chemical changes. So first one is burning methane. That's a clear chemical change. We are changing the chemical identity of our starting material. Melting ice. So melting ice, we're going from H2O solid, we're going from solid water to liquid water. What change is that? Is that a physical or chemical change? If it's a phase change, it's a physical change. Our chemical formula is unchanged. Now, our last example is filtering a solid precipitate from a solution. So this is a separation. Is this a physical change or a chemical change if we're filtering? Physical. Yep, exactly right. Perfect. So let's take a moment now and let's work on the following problem-solving session. I'd like you to classify the following three changes as physical or chemical changes. Let's take about 2 minutes to work through this example, and don't be shy to submit your responses via Canvas or using the chat feature.
Could you explain how filtering the solid is a physical?
Yes. So let's suppose, for example, you have some solid lead chloride and you have some water. And you filter it, and caught on your filter is your solid lead chloride. And after filtration, you just have some water sitting in your beaker. Has the chemical formula of our substances changed? Has our chemical formula changed during filtration?
No, not at all.
Yep. So then it's a physical change as a result.
Okay, thank you.
Does that make sense?
Yeah, perfect.
Perfect. Okay, so let's take about another minute to a minute and a half And let's write our proposed solution for problem solving session 1.101. Any other responses? Don't be shy to message your proposed solutions in the chat, and we'll discuss in about 30 seconds. So let's discuss now. So let's look at the first case. So gasoline evaporates. So we're going from liquid to gas. Is that a physical or chemical change? A phase change? Is that physical or chemical? Physical, yep. The next example, this is commonly done in titrations if you want more accurate results. Heating water removes some of the dissolved carbon dioxide. Is that a physical or chemical change if we're separating carbon dioxide from water? Physical, yep. In the last case, mixing two solutions yields, and this is a key word indicating a likely chemical reaction, a white solid precipitate. So if we mix two solutions together, we see a product form. Is that a physical or chemical change? Chemical, yep, exactly right. Okay, let's keep going now. So now we're going to deal with physical or chemical properties. So in this next guided example, I'll classify the following properties or statements as physical or chemical properties. So density. We've already established density is a physical property. Let's look next at the next statement. Alkali earth metals react violently with water. So we see the keyword react. Does that indicate a physical or chemical property? Physical or chemical? Chemical, yep. Hydrochloric acid is corrosive to the skin and many metals. So corrosive, does that indicate a physical or chemical property? Chemical, yep. Okay, so now that we've done a guided example together, let's open Canvas Quiz 1.10-2, and I'd like you to complete the following statements and classify the following properties as physical or chemical. Let's take about a minute to a minute and a half, and then we'll discuss momentarily. Let's try to get a few more responses in the chat, and we'll discuss momentarily. So let's start with the first one. Sodium chloride dissolves in water. So the key word dissolves, what does that tell us? Solubility, is that a physical or chemical property? Solubility, is that physical or chemical? Physical, yep. We're just going from solid to aqueous. In this next case, we see alkaline earth metals react with water to yield hydrogen gas. So the key word react tells us what? Physical or chemical? Chemical, yep. Perfect. So let's now continue on. So let's discuss the scientific method briefly. So what is the scientific method? Oops, one moment. There we go. So fundamentally, science is based on observations. Observations can be either collected data that we call quantitative observations or descriptions of phenomena that we call qualitative observations. A key feature of observations is that observations do not attempt to explain the collected data or phenomena. They're just our observations and any data collected about a natural phenomenon. So for example, just to illustrate this thought process and how we can take even a simple set of observations and start to make more sophisticated models. So let's suppose we have a balloon, and at room temperature, it looks something like this. If we take a balloon and we put it in the freezer at 0 degrees Celsius, we clearly see that the balloon shrinks. Now, a series of similar observations for a set of phenomena can lead to development of a scientific law. And scientific laws, quite simply, provide a summary of past observations, and they provide a prediction of future observations for a system. So they have some predictive power by virtue of how many observations you've gathered together. So Charles' law is a law relating to gas behavior, and it says as the temperature of a gas decreases, the volume of a gas decreases. So we can answer the question, what would we expect to happen to the volume of the gas in the balloon when the temperature decreases? So what would we expect to happen based on this idea that the volume is proportional to the temperature? What would we expect to happen? As the temperature decreases, we can clearly see that the volume decreases. Perfect. Okay, so we clearly see this law has predictive power and explains our observations. So from observations, outside of making a scientific law by compiling your observations together, scientists can formulate a hypothesis. And a hypothesis is an explanation for the collected observations. So a hypothesis has two major criteria. It has predictive power and it's testable via experimentation. So for our hypothesis is at high temperatures, gas particles move at higher velocities and impact the container walls with a greater force. So this is our explanation for why the balloon at high temperatures stays full. Now, experiments are carefully designed procedures designed to refute aspects of a hypothesis or provide supporting evidence for that hypothesis. Now, depending on the data collected, A hypothesis can be revised to account for collected data and observations, or it is discarded if it cannot be reconciled with collected observations. So this is a constant process of revision in response to collected experimental data and observations. Now, a well-supported hypothesis becomes the basis for a theory. And a theory is an overarching model for the way that nature is that tries to explain what nature does and why. It serves to explain our natural laws and observation. So the main theory that governs gas behavior is kinetic molecular theory, which explains observations of gas behavior under the ideal gas law. We'll learn more about kinetic molecular theory in chapter 5, where we cover gases. So this is how all of these different pieces fit together in the scientific method. Any questions so far? If not, let's keep going then. So let's talk about scientific notation. So science is based on observations, that much we've established. We often collect data by taking measurements using tools called instruments, okay? Now each measurement has a number and a unit. So 10 m or 10 meters. The number is a number that describes the amount of your unit that you have, and your unit tells you what standard unit of measurement are you counting in terms of. So when handling numbers in science, we often have to deal with very large or very small numbers. We are counting the number of atoms in a sample we can weigh, and there are millions upon millions of atoms in even samples with small masses. So as a result, we have to use scientific notation. And scientific notation is of the form blank times 10 to the n. So this blank must be greater than or equal to 1 and less than 10. Now your exponent can be any whole number power. So no decimals, and n can be negative or positive. Either would work. So let's do some examples of numbers in scientific notation. So an example of a properly written number in scientific notation would be 2.0 times 10 to the negative third. Now, here are some things not to do. Let's try to see some problems here. Would 1.0 times 10 to the 0.5 be okay? What's the problem with this? What's the issue? Why is this not okay? Yep, this n cannot be a decimal. Exactly right. What about this? I see this a lot. 0.9 times 10 to the second. What's a problem with this statement? Is this valid in scientific notation? What's a problem with this next set of numbers? It doesn't have to do with the exponent, but let's take a look at our number here, 0.9. Can we have a number less than 1?
The sig figs?
We haven't covered sig figs just yet, but it's actually the fact that 0.9, your number in scientific notation must be greater than or equal to 1 and less than 10. So it must be greater than or equal to 1. So in this case, this number is not okay. Just like, for example, if I report 10 times 10 to the negative fourth, is that okay in scientific notation? Is that reasonable to report? So looking at our criteria, can we have a number equal to 10 when writing numbers in scientific notation? No. So 10 is not okay because 10 must be less than 10. Okay, just as one last check, would 1.5, would 1.0 times 10 to the negative 6th be okay in scientific notation? Is 1.0 times 10 to the negative 6th okay? Yep. The numbers greater than or equal to 1, less than 10, our exponent is a whole number. Everything's good to go. Okay, so let's keep going now and let's talk about exponents. How do we deal with exponents? So we call the number that the exponent is being applied to the base, and the power that our base is being raised to is the exponent. Now, dealing with exponents, you multiply the base by itself n times, where n is our exponent. So for example, 10 to the second, we multiply 10 by itself 2 times. Now, for powers of 10, there's a nice trick. You move the decimal point n spaces to the right if n is positive. So let's show what I mean by that. So if we have 10 to the 7th, so 10 to the 7th, we put our decimal point at the end and we're going to move it over 7 spaces. So 1, 2, 3, 4, 5, 6, 7. So that gives us one more 0 then added. 10 million, there we go. So this is a quick trick when you're multiplying or dividing by powers of 10. If it's a positive power of 10, you move your decimal point n spaces to the right. In this case, n is 7, so we move it 7 spaces to the right. Does that make sense to everyone? Okay. So for negative exponents, one thing that you need to keep in mind is that 10 to the negative n is equivalent to saying 1 over 10 to the n. So multiplying by something raised to a negative exponent is the same thing as dividing by something raised to a positive exponent. So for example, 10 to the negative third is equivalent to 1 over 10 to the third, which is equivalent to 0.001. Now, just like positive powers of 10, there's a shortcut for negative powers of 10. You move the decimal point n spaces to the left if n is negative. So for example, 10 to the negative fifth, we put our decimal point at the end, and what we're going to do is we're going to move our decimal point to the left 5 times. So we have 1, 2, 3, 4, 5. So we have 0.0001 as our final output. Does this make sense to everyone? Okay, let's continue on then. So for writing numbers in scientific notation, first and foremost, you write the number and you place a decimal point at the end of the number if there is no decimal point. So let's suppose, for example, we have the number 4,573. We'll just put a decimal point at the end of it. Now, what we have to do now is move our decimal point until the number is greater than or equal to 1 and less than 10. So let's keep moving our decimal point now. So if I move it over one space, is that enough? Do we have a number between 1 and 10? No. So let's try one more time. Now do we have a number between 1 and 10? No. So let's try one more time. Now do we have a number between 1 and 10? Yes. So we'll write this as 4.573. Now, we want to make sure that we count the number of spaces that the decimal point was moved. So let's do that just now. How many spaces did we move our decimal point? Well, we see we moved it 3 spaces. So we moved it 3 spaces in what direction? To the left or to the right? To the left. Okay, so now that we have that information in hand, what we're going to do now is our power of 10, n, is positive if your starting number is greater than 1. So n is the number of spaces that you move to the left. So this would be 4.573. Since we moved 3 spaces to the left, it would be 10 to the third. In general, if your starting number is greater than 1, n will be positive. If you had to move your decimal point to the right, n is -1 times the number of spaces moved to the right. N is negative if your starting number is less than 1. So to show an example of that, let's suppose we have 0.0375. We'd have to move our decimal point 2 spaces to the right. And as a result, we'd write our number as 3.75. And then since n is negative times the number of spaces moved to the right, we'd have -2. So 10 to the -2nd power. Does this make sense to everyone? Okay, so let's keep going now, and this time we'll do a few guided examples where I'll convert the following set of numbers into scientific notation. So first and foremost, we have 4,534. I'm going to place the decimal point at the end, and then I have to move it over 1, 2, 3 spaces. That in turn gives us 4.534. And since we moved it 3 spaces to the left, we moved our decimal point 3 spaces to the left. Are we going to have a positive or negative power of 10? Positive or negative? Is it going to be +3 or -3? It's going to be positive. So it would be 4.534 times 10 to the third. Okay, let's deal with a small number. If we have 0.0034201, we're going to move our decimal point 1, 2, 3 spaces. So 3 spaces to the right. So that gives us 3.4201. And our power of 10 is going to be negative. So it would be times 10 to the -3rd. Perfect. So what you're now going to do is you're going to convert the following numbers in this problem solving session into scientific notation. So take a moment and convert the following set of numbers into scientific notation. You're welcome to submit your responses via Canvas or using the chat function that we have in Zoom. and we'll discuss in about 2 to 3 minutes. And don't be shy to message your responses via Canvas or in the chat feature. I'd like to see a few responses before we discuss this next set. Let's try to get a few more responses in the chat, and then we'll discuss in about a minute to a minute and a half.
So just for to clarify, are all of the quizzes on that we can see right now, are those for just this week?
Just for this lecture note set. These
Okay,
are
so,
posted. Yeah, so all the quizzes currently posted are for the chapter 1 note set. There'll be additional ones posted for chapters 2, 3, 4, etc. And you can tell by the number in front will be the note set that the quiz is based on. Does that make sense?
yes, thank you.
Okay, perfect.
And just to be sure, these are all due at the end of the week, right?
Yep, exactly right.
Okay, cool.
So let's address the following problem. So I saw some reasonable responses for this first number here. So let's write out our number, which is 0.037. Now, in order to get a number between 1 and 10, we need to move our decimal point 1, 2 spaces to the right. So we indicate 2 to the right. And we write this as 3.7. Since we moved our decimal point to the right, we're going to have a positive or negative exponent. Positive or negative exponent. Negative. So it'd be 3.7 times 10 to the negative second. Good, good. Okay, let's look at this next number here. So we have 15.607. So we have to move our decimal point 1 space to the left. And that in turn gives us 1.5607 times 10 to the first. Perfect. Any questions on this example? Any questions on this example before we move on? Okay, let's keep going then. Let's now try to convert a set of numbers to a decimal. So we have 3.70 times 10 to the fourth. So I'm going to take my decimal point, and since I have a positive exponent, I'm going to move my decimal point to the right 4 spaces. So 1, 2, 3, 4. And that in turn gives us 37,000. Let's look at another example where we have a negative exponent. So we have 0.105 times 10 to the negative second. So we write out our number. And since we have a negative exponent, we're going to move our decimal point to the left 2 spaces. So we have 0.00105 as our decimal answer. Do these examples make sense so far? Any questions so far? So what we're going to do now is we're going to take about 2 to 3 minutes and we're going to work on completing the following problem solving session 1.12-1. And don't be shy to submit your responses via Canvas or message me your proposed responses using the chat function. And we'll discuss in about 2 to 3 minutes. And I'd like to see a few more responses in the chat before we discuss. Don't be shy to write out the long form numbers via chat, and I'll be checking Canvas to see how everyone's doing in terms of the responses. Oh wow, we have, oh whoops, that's the previous quiz. Let's try to get a few. Let's try to get a few more responses in the chat. Oh, sorry, this is 1.12-2. Let me just correct that really quickly if you're entering it into Canvas. So I see plenty of responses via Canvas. So let's try to discuss these examples as I see a lot of perfect responses via Canvas. So let's first look at the following number. We have 0.00435 times 10 to the 6th. So we're going to write out our number 0.00435, and then we're going to move our decimal point to the right 6 times. So we have 1, 2, 3, 4, 5, 6. So that in turn gives us 4,350, in other words, 4.350 times 10 to the 3rd. Of course, since I asked you to convert this number to a decimal, you'd write out this long form number. Everything makes sense so far? It matches exactly how most of the class responded in the Canvas quiz. So let's look at this next example. We have 20,190 times 1 over 10 to the 3rd. That's equivalent to saying we have 20,190 times 10 to the negative 3rd. We're going to write out our number, place our decimal point, and since we have a negative exponent, we're going to move our decimal point 3 spaces to the left, and that in turn gives us 20.19 as our final answer. Does this make sense so far? Any questions so far? Any questions before we move on to the next topic?
Yeah, I'm sorry. Can you do that again? Do it again. I'm confused.
Which one?
Both of them. I don't understand.
So if we're asked to convert the following numbers into a decimal, so we have 0.00435 times 10 to the 6th. So we have we're multiplying by a positive power of 10. So what we're going to do is we're going to write out our number, which is 0.00435. And since we have a positive power of 10, we're going to move our decimal point 6 spaces to the right. And that in turn gives us 4,350. Does that make sense? When you multiply by positive powers of 10, you move your decimal point to the right. If you multiply by negative powers of 10, you move your decimal point to the left. Does this first example make sense?
No, I'm still confused. But I mean, I kind of understand it, but how does it end up 4,350?
So
Or like 4.350?
Oh, the 4.350 times 10 to the third?
Yeah, that part.
Okay. So this is the 4,350 is the number that you'd report normally. If you wanted to write this number in scientific notation, you'd take your decimal point, you'd move it to the left 3 times, and that would give us 4.35. And then since we moved our decimal point to the left 3 times, we'd write it as 10 to the third. This is just helping to check your work. I always like to rewrite my answer in scientific notation.
Okay.
I find it easier to multiply powers of 10 rather than a decimal point around multiple times. And this is just to tie it back. And this is just what I use to check my work. Does that make sense?
Yeah, it does. Thank you.
Okay, perfect. And just for the second example, one more time. So we convert, if we're dividing by a positive power of 10, that's equivalent as multiplying by a negative power of 10. And now what we're going to do is, since we're multiplying by 10 to the negative third, we'll move our decimal point 3 spaces to the left, and that gives us 20.19. If we wanted to write 20.19 in scientific notation, we'd move our decimal point 1 space to the left, and that would give us 2.019 times 10 to the first. Since we moved our decimal 1 space to the left. Do these examples make sense? Did that clear up any questions?
So, would the answer be 4,300, just what you have squared?
Yep. Any other questions I can address before we move on to another topic? Really don't be shy to ask. If not, we'll continue on to the next topic. So let's talk next about units of measurement. So units really do provide meaning to numbers by indicating what you are measuring and what standard unit of measurement you are using. For example, 10 meters tells us that we have 10 of the standard SI unit of a meter. Now The United States, unfortunately, uses the imperial or English system of measurement, but the sciences use the metric system. Now, you may ask, why should I care about unit conversions? And this is not making fun specifically of the engineers, but it's a pretty clear case of unit conversions not being checked. Pictured below, this is pretty infamous. Most textbooks talk about it. It's the crash site of the Mars rover. I always like to ask, is it 10 feet or 10 meters below the surface of Mars? Who knows? A NASA review board found that the problem was in the software controlling thrusters. It calculated the force required to exert in pounds of force. A separate piece of software took in the data, assuming that it was in the metric units of newtons. Now, propulsion engineers typically like to express force in pounds, and it's standard practice to convert to newtons for space missions. 1 pound of force is about 4.45 newtons, and an unfortunate error is that the engineers at JPL assume the conversion has been made and they didn't check. Now, the reason why I like this story is it's a lesson also that when you go through and you solve a problem, just go back and check your work once in a while. It can save you a lot of grief. So, let's talk a little bit about unit conversions. So the metric system is based on powers of 10, and as a result, scientific notation is particularly useful. The metric system is underpinned with the concept of base units, where we have distance in meters, mass in grams, volume in liters, time in seconds, and temperature in kelvins. Now, to indicate large or small quantities of a unit, the metric system uses common prefixes. It uses prefixes. Now, each prefix has a unique symbol. Now, the prefix modifies the base unit to give a prefix unit. So for example, each prefix corresponds to a power of 10. So a centimeter, this centi prefix tells us we have 10 to the negative second meter. Each prefix corresponds to a power of 10. So for example, centi corresponds to 10 to the negative second. Milli corresponds to 10 to the negative third. Kilo corresponds to 10 to the positive third. Now, the reason why I like prefix unit conversions is that if you want to convert a prefix unit to a base unit, you simply replace the prefix with the power of 10. So let's try this as an exercise. So what power of 10 does the milli prefix correspond to? What power of 10 does the milli prefix correspond to? Looking at this table. And this is one that you'll have to memorize for most exams. Milli corresponds to 10 to the negative third. And do we know how to multiply by powers of 10? Do we know how to multiply by powers of 10? Yeah, we do, right? So we take 657, and since we're multiplying by a negative power of 10, we move our decimal point 1, 2, 3 spaces to the left. And that in turn gives us 0.657 meters. Does that make sense to everyone? You can also rewrite this number as 6.57 times 10 to the negative first meters if you're used to combining powers of 10 rather than moving the decimal point. Both methods are valid. Let's look at another.
You'll
Yeah.
let us know, right, whenever you want it in scientific notation?
Yes, yes.
Okay, cool.
I find often from a bookkeeping perspective, it's easier to write numbers in scientific notation,
Yeah, definitely.
especially when we start dealing with significant figures.
Right, right. Okay, thank you.
So let's do another example. 457 kilograms. What does the kilo prefix correspond to?
Ten to the positive third?
Yep, exactly right. So then we take our number of 457, we put our decimal point at the end, and we move our decimal point 3 spaces to the right. So we have 457,000 grams, which we can rewrite as 457. Oh, let me do this. 4.57 times 10 to the 5th grams. Just another method that some students like is they like to write out their starting number in scientific notation, and then they like to multiply their powers of 10. And when you multiply powers of 10, you just add them together. And that gives you 4.57 times 10 to the 2 plus 3, which is 5. These are two methods that I commonly see that are pretty efficient for these types of conversions. Does this make sense? Does the idea behind prefix to base unit conversions make sense? Is everyone comfortable with this idea? So we've established very clearly it's easy to go from a prefix unit to a base unit. Wonderful. We'll exploit that idea in a moment. So one fundamental idea behind unit conversions that you really have to see to get is different units and numbers can describe the same quantity, the same thing in our physical world, right? Centimeters and inches describe distance, right? And we know that 2.54 centimeters are equal to 1 inch, right? We see it physically in this chart right here. 2.54 centimeters, which is right here, equals 1 inch, which is above here, right? So these two numbers and units are representing the same distance, right? Everyone sees how the red lines line up exactly. Now, what we can do is we can write unit conversions as a ratio of two equal quantities. So if we know 2.54 centimeters equals 1 inch, I'm going to divide both sides by 1 inch, and that gives us 1 is equal to 2.54 centimeters over 1 inch. We can also write the inverse, where 1 is equal to 1 inch over 2.54 centimeters. These are the two conversion factors that we can build from this equality. Notice, always write your number, always write your units. Does that make sense? Now, this is built on ideas from math, which is you can multiply any quantity by 1 and the quantity is unchanged in value. Of course, the units and the number change when you convert between different units, but the value, what it's actually representing in our physical world, does not change. So when you multiply and divide by unit conversion factors, the units will cancel just like normal numbers. So for example, 7 times 2 over 7, we can cancel out the 7. It's the same number or variable on the top and bottom of our equation. So if we wanted to figure out 2 centimeters are equal to how many inches, we'll take 2 inches and multiply it by our conversion factor. We notice inches cancel and we're left with units of centimeters. If your unit conversion is set up properly, your desired units will be on top and your starting units will cancel out. Now, you really want to make sure the units cancel. This is commonly seen with square or cubic units that students don't completely convert all of the units. So one tip I have for you is to write out all of the units associated with a number. So 5 centimeters squared is 5 centimeters times centimeters. Make sure to break apart your cubic or square units into the pieces so that way you don't forget to complete your conversions. Okay, so let's do a guided example and let's do a how-to guide, how to convert from one unit of measurement to another unit of measurement. And we're going to phrase this in terms of solving a question. So how many milligrams are in 3.46 times 10 to the first kilogram? Okay, so first indicate what units we are starting from. What are our starting units? What units are we starting from in this problem? What units are we starting from? Kilograms. So let's put that down. Okay, what units are we trying to convert to? Milligrams. Okay, so some students love to go directly from prefix to prefix. I would recommend against that and just go through the base unit. So what is our base unit? What base unit are we going to go through to make our lives easier? What's our base unit in this case? Grams. Okay, perfect. So now I have this nice solution map that tells me exactly what units I'm going to have at each step. And all I have to do is figure out the conversion factor that gets me there. So in this first example, I want to go from kilograms to grams. So what's our relationship? So kilograms and grams, what's our relationship? So 1 kilogram is how many grams? 1 kilogram is how many grams? Kilo tells me what? What is kilo representing? What
10
power?
to the, 10 to the positive third?
Yep, exactly right. 1 kilogram is 10 to the third grams. So do we have an equality to work with now?
Yes.
Okay. So now, as a rule of thumb, when I draw my arrow for my conversion scheme, the desired unit will be on top and the starting unit will be on the bottom of our conversion factor. So then, what should I put on top? Which quantity should I put on top in my conversion factor? Grams or kilograms? What goes on top? Grams or kilograms?
You want to first get to grams?
Yep, so we're going to put grams on top. So we're going to put 10 to the third grams on top. And what unit are we going from? What unit are we going to put on the bottom of our conversion factor? Kilograms, exactly. So now we have a conversion factor with our desired unit on top and our starting unit on the bottom. So we're just going to put a box around that. Perfect. So if we wanted to do this conversion, we'd convert from our starting prefix unit to the base unit by multiplying by our conversion factor. So let's write out our starting number with our unit. So we have 3.46 times 10 to the first kilogram. And we see that if we multiply by our conversion factor, which is 10 to the third gram over 1 kilogram, kilograms will cancel and we're left with 3.46 times 10 to the fourth gram. I know this method may seem a little procedural and steppy, but does everyone understand does everyone see how clearly your thought process is laid out in this method? Does this method make sense to everyone? Okay, so let's continue on. We're not quite done yet. We have to identify a conversion factor containing our desired prefix unit and the base unit. And one rule that I always want you to keep in mind, you always keep the power of 10 with the base unit. Okay, so let's try. We went from kilograms to grams, and now we're going from grams to milligrams. So grams to milligrams. So let's develop, oh, yep, I'll go back up. One moment. Is everyone good now? Did that address that comment?
Yes, thank you.
Okay, perfect. Okay, so now we're going from grams to milligrams. So again, let's develop our relationship. So 1 milligram is equal to how many grams? What does the milli prefix correspond to? What does the milli prefix correspond to? 10 to the negative third. I always like writing things out in terms of powers of 10 because they're easier to multiply and divide by. Okay, now if I'm going from grams to milligrams, what unit am I going to have on top of my conversion factor? What unit am I going to have on top of my conversion factor? Grams or milligrams? If I'm going 2 milligrams, I'm going to have milligrams on top. Exactly. So if I'm going from grams, what units am I going to have on the bottom? Grams, exactly. And remember, the power of 10 always stays with the base unit. This is where I see really odd errors in creating conversion factors. The beauty of this method is that the power of 10 will always be next to the base unit. So now all we have to do is convert from the base unit to the desired prefix unit. So we have 3.46 times 10 to the 4th grams. Let me just check to make sure that's right. Yep, that matches our output. And we multiply by our conversion factor, which is 1 milligram per every 10 to the negative third gram. Grams cancel, and we're left with 3.46 times 10 to the 7th milligrams. Does this make sense to everyone? Okay, so just to show this long form here, if we start off with 3.46 times 10 to the 1st kilograms, and we're going from kilograms to grams to milligrams, first things first, we multiply by our first conversion factor, which has grams on top and kilograms on bottom. So we have 10 to the 3rd gram per every 1 kilogram. Next, we're going from grams to milligrams. So we have milligrams on top, grams on the bottom, and then we just multiply everything out. Kilograms cancel, grams cancel, we're left with milligrams. Now, the reason why I like this logic behind unit analysis is because you can solve problems just by looking at the units. The majority of the problems encountered in this class can be solved just by writing out the units and developing a logical conversion factor to convert between your units. So it's a beautiful tool for checking your work and understanding and rationalizing a lot of the equations encountered in this class. Especially if you're taking physics, if you know how to do unit analysis, you can memorize most of the formulas quite easily. So since these conversion factors are metric to metric, you'll be responsible for knowing them for all the exams. I believe these are also covered extensively in the prerequisite chemistry course as well. Yes. Oh,
When
do you have a
when
question?
yeah, when showing our work, do you mind if we not go to the like go to grams, if we can just go from kilograms to milli?
If you're comfortable doing that, I'll certainly accept it. Although I would caution that that does have the potential to introduce error. And the more you're able to write out the intermediate units, the easier time you'll have in later sections where we're doing conversions between mass, moles, and atoms, for example. And
Okay.
that's what this framework is trying to develop.
Yeah, just so you can like cancel out whatever you don't want and
Yep.
just keep what you want.
Yep.
Okay.
Any English to English and metric to English conversions you will be given, but these metric to metric conversions, such as the one we used in this example, you'll have to know. Does that make sense in terms of the expectations?
So for the chart that you gave us, we have to know everything like up to pico and mega.
Yep,
So
exactly.
from top to bottom. Okay, cool.
Mhm.
I have a question.
Yes.
Why is it 10 to the 7th? Is it going back to that chart where we need to memorize?
So the 10 to the 7th is the result of multiplying powers of 10. And I'm glad you asked this question because this is a good place for me to showcase this. So when you multiply powers of 10, first things first, we write out all of our powers of 10 on the same line. So 1 over 10 to the negative third is equivalent to 10 to the third. Okay? So do you see where I got all of my powers of 10 from? Does it make sense where this 10 to the first, 10 to the third, and 10 to the third came from?
Let's see. Yes.
Okay, perfect. So now that we have our powers of 10, when you multiply powers of 10, you simply add these numbers together. So that gives us 3.46 times 10 to the 1 plus 3 plus 3, which is 3.46 times 10 to the 7th. Does that make sense?
Yeah, well, it doesn't matter if it's negative 3, so you'll always be adding it.
The negative was on the bottom. So 1 over 10 to the negative third is equivalent to 10 to the third.
Okay.
You can move a power of 10 on the bottom to the top if you multiply this power by -1. This is a property of powers of 10. And that's where we got the 10 to the positive third from. Another way you can do this is in your calculator. If you manually enter each of these inputs, your calculator will process the powers of 10 for you as well. Or you can write out each of these powers of 10 as a decimal and then enter those into your calculator. All of those methods are valid, and whatever you prefer or comfortable with, you're more than welcome to use. Does that make sense? Perfect. Any other questions I can address? So let's do another guided example. I'll do 2 of them for you. We're asked how many nanometers are in 4.5 times 10 to the 4th picometer. So first things first, we identify our starting unit, which is picometer, right? It's the unit attached to a thing with a number next to it. So we have picometer, and we want to get to nanometer. So what is the base unit that we're going to go through? What is the base unit that we're going to go through? What base unit? Meters, exactly. Okay. So let's write some equalities up here. So 1 picometer is equivalent to how many meters? What does the pico prefix correspond to? What does the pico prefix correspond to?
10 to the negative 9.
That is nano.
Oh, yeah. Sorry, you're right.
Pico is
But-
negative 12, but
Well,
we'll write nano as well. 1 nanometer is 10 to the negative 9th meter. Perfect. So now that we have our two equalities in place, we'll leave them off to the side for now. And next we'll write out our number and our unit. And let's assemble our first conversion factor. So we're going from picometer to meter. So what units do I want on top for our first conversion? What units do I want on top for our first conversion? Where is our arrow pointing? Where is our arrow pointing to? What are we trying to convert to? Meters. So we're going to put meters on top. And where's our arrow going from? Where are we going from? Picometers. So we put picometers on the bottom. We always put a 1 next to our prefix unit. And what power of 10 corresponds to a picometer? What power of 10 do we put? Yep, 10 to the negative 12th. Picometers cancel. Okay, so we've done the first part well. Let's do a one-line conversion. So next we're going from meter to nanometer. So what units need to be on top for our second conversion? What units need to be on top? Nanometer, yep. And what units are on bottom? Meter, yep. So 1 nanometer corresponds to how many meter?
10 to the negative 9.
Yep, exactly. So now we do a check. We see picometers cancel, meters cancel. We're left with units of nanometer. So I'm going to write out the answer right here, and I'll show the power of 10 analysis below. This would be 4.5 times 10 to the first nanometer. So to show how that works, we have 4.5 times 10 to the fourth times 10 to the negative 12th. This 1 over 10 to the negative 9th is equivalent to 10 to the positive 9th. So if we multiply our powers of 10, that's 4.5 times 10 to the 4 minus 12 plus 9, which in turn gives us 4.5 times 10 to the first. Does this make sense to everyone? Does this logic make sense? Any questions on this example? So let's do another one now. And let's ask how many centimeters are in 0.5 times 10 to the negative third millimeter. So our starting unit is millimeter. We're trying to get to centimeter, and we're going through meters. So let's set up some equalities. 1 millimeter is how many meters? Milli corresponds to what? Ten to the negative third, exactly right. 1 centimeter corresponds to how many meters? What does centi correspond to? 10 to the negative second. Okay, so now let's write out our number. We have 0.5 times 10 to the negative third millimeter. So we're looking at our guidelines from millimeter to meter. So what units need to be on top? Meters, yep. And what units do we need on bottom? Millimeter, yep. And what power of 10 do we put next to meters? What power of 10 do we put? What power of 10 corresponds to milli?
10 to the negative third.
Yep, exactly right. So next, what we're going to do is we're going to convert from meters to centimeters. So then, what units do we need on top? What units do we need on top? Going from meters to centimeters, what units do we need on top?
You want centimeters at the end?
Yep, exactly. And then what units do we want on the bottom?
The base meter?
Yep. So we have 1 centimeter, and what power of 10 corresponds to a centimeter?
10 to the negative 2?
Yep. Okay, so let's check our units cancel. They do. And if we punch this into our calculator, we'll get 0.5 times 10 to the negative fourth centimeter. So just to show our power of 10 analysis, we'd have 0.5 times 10 to the negative third times 10 to the negative third. This 1 over 10 to the second, 1 over 10 to the negative second corresponds to multiplying by 10 to the positive second. And that in turn gives us 0.5 times 10 to the negative fourth centimeters, which we can write as 5 times 10 to the negative fifth centimeters if we want to write our number in scientific notation. Does this make sense to everyone? Okay, so let's now have everyone work on a few problem-solving session examples. So let's try to answer the question, how many microliters are in 153 milliliters? And answer the question, how many milligrams are in 457 micrograms? So take a few minutes to work on these examples, and you're more than welcome to submit your responses using the Zoom chat or via the Canvas quiz module. And I'll give everyone about 5 minutes to work through these two examples. And I'll be checking responses via Canvas or the Zoom chat. And don't be shy to message me with questions. Oh, no problem. The first question is going fine. I'm seeing an array of answers for the second. We'll discuss in about 3 minutes. And don't be shy to message me your proposed responses via the Zoom messaging or through the Canvas quiz function. And we'll discuss in about 2 minutes. And we'll discuss in about 1 minute. I'm seeing a fairly robust range of responses. Then the majority of the responses look quite good in the Canvas submission. And we'll discuss in about 1 minute. And don't be shy to also type your proposed responses via the chat function. So let's look through the first example. So we're starting off with units of milliliters. We are trying to convert to units of microliters, and our base unit is liters. So let's write some equalities down. 1 milliliter corresponds to how many liters? What does the milli prefix correspond to? What does the milli prefix correspond to? 10 to the negative third. Yep. Finally, we're also dealing with liters and microliters. So 1 microliter corresponds to how many liters? What does the micro prefix correspond to? 10 to the negative sixth. Perfect. So now that we have both of our equalities in hand, let's write out our number in units. We have 153 milliliters. So we're going from milliliters to liters. So what units do we want on top? What units do we want on top? If we're going from milliliters to liters, what units do we want on top? Liters, yep. And what units do we want on the bottom? Milliliters. So what power of 10 do we put next to the liters on top? What power of 10 corresponds to 1 milliliter? What power of 10? 10 to the negative third, yep. Next, we're going from liter to microliter. So what units go on top? What units go on top? Microliter, yep. So 1 microliter corresponds to how many liters? 1 microliter corresponds to how many liters? 10 to the negative 6th, exactly right. Our units cancel, and we're left with 153 times 10 to the 3rd microliter, which is equivalent to 1.53 times 10 to the 5th microliter, or 153,000 microliter, whatever you prefer. Just to show the power of 10 analysis, we have 153 times 10 to the negative 3rd times 10 to the positive 6th gives us 153. Whoops, one moment. Let me reopen OneNote. Oops. Okay, so resuming our discussion. So just to show the power of 10 analysis, we have 153 milliliters times 10 to the negative 3rd times 10 to the positive 6th. That in turn gives 153 times 10 to the 3rd microliter that we can write as 1.53 times 10 to the 5th microliter. Or 153,000 microliters. All are valid. So let's look next at a conversion from micrograms to milligrams. So we're starting off with micrograms and we're converting to milligrams, going through our intermediate unit of grams. So starting off with 457 micrograms, let's write some equalities. So first and foremost, 1 microgram corresponds to how many grams? What corresponds to a microgram? 10 to the negative 6th, exactly right. And 1 milligram corresponds to 10 to the negative 3rd gram. Okay, so 457 micrograms, we're going from micrograms to grams. So what units do we put on top? What units do we put on top? Grams, yep. And micrograms go on the bottom. And what power of 10 again matches a microgram? What power of 10 do we put on top? 10 to the negative 6th. Okay, next we're going from grams to milligrams. So what units do we put on top? Milligrams. So 1 milligram corresponds to how many grams? 10 to the negative 3rd, exactly right. We check our units cancel, and that in turn gives us 457 times 10 to the negative 3rd milligrams, which is equivalent to 0.457 milligrams. So just to show the power of 10 analysis, 457 times 10 to the negative 6 times 10 to the 3rd is equal to 457 times 10 to the negative 3rd, which is equivalent to 0.457 milligrams. Do these two examples make sense so far? Okay, so we'll stop today's lecture here for today, and we'll resume tomorrow during our scheduled lecture time. I'd like you to use the remaining time in this laboratory period to look over the pre-lab for lab 1 that we'll be working on tomorrow and getting the lockdown browser tested and set up and getting everything registered for mastering chemistry. I'll be adjusting the due dates momentarily for assignments in mastering chemistry and just correcting any potential due date errors.